I think you have to maybe start it. Okay, so let's start the seminar. It's a great pleasure to have Yunqin Zheng from Kavli IPMU in Tokyo, and he'll talk about Symmetry TFT for non-invertible duality defects. So please take it away.
All right. Thank you very much for giving me the opportunity to speak here. And today I'm going to talk about the Symmetry TFT for non-invertible duality defects. So this talk is based on work in collaboration with fantastic collaborators on Justin Kaidi, Kantaro Omori, and Gabi and Safari. So let me start by talking about global symmetries. So there's no doubt that global symmetry is very useful. First of all, it provides us an organizing principle of studying the operators and the states in the quantum field theory. And also, especially when there is a 't-Hooft anomaly, the global symmetry together with the 't-Hooft anomaly provides strong constraints on the dynamics. The concept of the global symmetry in recent years has been vastly generalized thanks to the modern understanding, which is that the global symmetry can be understood as the presence of topological operators or defects. So the generalization is mainly in two aspects. And first, the defacto dimension. So usually we only consider the defacto dimension to be one. And in recent years, we start to talk about the defacto dimension to be higher than one. So we put the word higher in front of the symmetries. Another direction of generalization is the defect to be non-invertible. So originally, we only talk about the defects which are invertible and which are associated with the group elements. But recently, people have been starting to talk about the defects which are non-invertible, and they are labeled by some objects in the category. So this is why we call it the categorical symmetry. And we can also talk about when the defect's codimension is higher than one, and also the defect is non-invertible, then we will have the higher categorical symmetry. And in this talk, I'm going to mainly focus on the categorical symmetry, but we'll also encounter examples of the higher categorical symmetry. Okay, so.
May I ask a question or make a comment on
Sure.
About the higher groups? I might already view something like a higher group as a categorical symmetry because I would view a higher group as categorical already, even though it's not invertible. Is this a good notation? Or?
Well, I think the defects even in the higher group associated with the higher group are also invertible. So I would call it an invertible symmetry.
I agree with that, but it's more about the categorical, isn't it? Already categorical. You know, a two-group is a category.
Yeah, but anyway, so we can view the higher group or higher form symmetry as a special case of higher categorical symmetry, and from that general aspects, I would agree.
Yeah. Okay.
Yeah. Thanks for the comment. So in recent years, people find that the non-invertible symmetry has appeared in many familiar quantum field theories in various dimensions. In 1+1D, it's well known that these non-invertible symmetries can appear as the Fluidity lines in the rational quantum field theory, rational conformal field theory. It can also appear in various statistical lattice models, also in the compact bosons and adjoint QCD and many other models. For example, I guess the simplest example is the Ising fusion category, where there are three objects, 1, eta, and n, and they satisfy this fusion rule. And it's from the fusion rule, it's obvious that this operator n, which implements the Kramers one-year duality, is non-invertible. And in 2+1 dimensions, non-invertible symmetry can also appear in various gauge series. The simplest one is the topological transcendent series, and the Wilson lines in the transcendent series can be viewed as the symmetry operators for the higher categorical one symmetry. But in recent years, people realized that even when adding the matters which makes the topological series non-topological, then some non-invertible defects survives as well. For example, when the gauge group is among these category, then there are non-invertible defects in the series. And in 3+1 dimensions, they also the non-invertible symmetries can also appear in various models, like the lattice statistical models, the Maxwell series, the Yang-Mills series with and without supersymmetries, QEDs, QCDs, axial models, and many others. So as you can see that especially in the recent 3 or 4 months, there are tons of papers talking about this, discussing this subject. Okay, and the non-invertible symmetries can also appear in higher dimensional series, and I'll not list them here. Okay, so far, the non-invertible symmetries, especially in higher dimensions, mostly come from the following constructions. So we first start with a QFT with the invertible symmetry, and we do something with the invertible symmetry to generate the non-invertible defects. So what is something? I'm going to list 5 possibilities of something. Something includes, first, we can gauge with a mixed anomaly. So this approach will give us the duality defects or triality or unality defects. But let me, for simplicity, just use the duality defects. So more concretely, we start with a series X with the invertible symmetry with the group G times H, and with a particular choice of mixed anomaly. And if we gauge the H, and the defect of the G defect in the QFT, in the gauged series, which I label as the X mod H, becomes non-invertible. There are pros and cons of this construction. And the advantage of this construction is that it's easy to apply this algorithm to generate many examples of non-invertible symmetries. So we simply need to start with a QFT with this group-like symmetry and with a specially designed mixed anomaly. And we just gauge one of the symmetries. And the gauged series automatically have this non-invertible symmetry. So we can use this algorithm to generate many examples, including the familiar example like QED and QCD. And also it's stable. The defect is kind of stable in the sense that as long as we perturb the series in X, which respect the G and H symmetry. And because the defect in the gauged series only depends on the symmetry anomalies, so this non-invertible defect is stable under this perturbation. Okay, but there are disadvantages of this construction, which is that by definition, this kind of defect is not intrinsically non-invertible, meaning that whenever you have a non-invertible symmetry constructed in this way, you can always gauge back to the original series, which only has an invertible symmetry. The second option of something is gauging on half space, which will also give us the duality defects. More concretely, if we assume that the QFTX, which is with the symmetry G, is invariant on the gauging G, namely X is X mod G, then the non-invertible defect or the duality defect can be constructed by gauging on half space and impose the Dirichlet boundary condition at the defect locus. There are also pros and cons of this construction. And the pro is that the defect can be intrinsically non-invertible. So there might not be a some gauging operation which maps the theory to another theory where the other theory only has invertible symmetry. But the disadvantage of such a construction is that, so the disadvantage of this construction is that the theory satisfying this property is kind of very limited to find. So far we know the example like the free Maxwell theory with some special choice of the coupling constant, and n equals to 4 super Yamil theory with some special choice of coupling constant. And it's not easy to turn on some perturbation which preserve this self-duality condition. So the theory that satisfies this condition, it comes in discrete ones, so not continuous families. Okay. And there is the third option, which is gauging outer automorphism. And this will lead to a higher categorical symmetry. And to be more concrete, we start with the QFT with an invertible symmetry. And the invertible symmetry contains the zero form part and a higher form part. And the zero form part acts non-trivially on the higher form part. And then if we gauge the zero form symmetry, then in the gauged theory, the higher form symmetry will become non-invertible. This has been nicely discussed in this paper, especially in higher dimensions. And the fourth option is the higher gauging, and this will give us the condensation defects. So more concretely, we'll start with the QFTX with the invertible symmetry G, and we gauge the G only on a manifold, with codimension equal or higher than 1. And finally, we can combine the second one, which is the gauging half space, with the higher gauging, and namely the higher gauging only on half a higher codimensional space. And this will provide us the higher duality defects. And we'll encounter an example of it later in the talk today. Okay, so why do we care about the non-invertible defects? Let me focus.
Question?
Yeah, sure.
Could you comment on the relationship between these different methods? Can they overlap in cases?
Yeah, so the relation between the first two methods are kind of clear. I would say that the second one, okay, so they cover different examples, and the advantage of one is the disadvantage of the other. And this approach is sort of relatively independent, and it can produce the first and second one are produce the non-invertible defects of codimension 1, and the third one produce the defects of codimension higher than 1.
But you can also, there are overlapping cases too, right? And for example, you get pin plus that can be described both with mixed anomalies and with gauging.
Yeah, as you discussed in the paper.
Yeah, maybe a related question. So could I ask about your definition of intrinsically non-invertible? Is the definition that you can obtain that theory by gauging a zero form symmetry? Or could it,
either zero form
or could it be any higher group symmetry?
Yeah, it can be any higher group symmetry.
Okay, great.
Yeah,
thank you.
Yeah, no problem. Okay, so let me continue. So people are interested in the non-invertible symmetry, especially the duality defect. and one reason is that it provides constraints on the RG flow, and this has nicely been discussed in this paper. So the main idea is that if the QFT in the UV is invariant under gauging G, this will also be true in the IR because this is the symmetry, and symmetry should be preserved on the RG flow. And moreover, because the IR theory can be classified, especially in the case when IR theory is invertible, is classified by the GSPT. So we can just plug in the classified series and check whether this equation is satisfied. If this condition is satisfied, namely the SPT is invariant under gauging G, then it means that this duality symmetry is anomaly free. Otherwise, it's anomalous. So one can use this idea to generate many theorems, and here is the one. Okay, so this motivates us to ask the following question. So can we understand the RG constraints of the duality defects from the invertible ones by using a topological manipulation, phi? So namely, can we find that topological manipulation phi, when act on this non-invertible symmetry, give us an invertible one? And phi can be gauging a symmetry and also stacking a SPT and etc. So here's the schematic diagram to illustrate the idea. So if we have a theory in the UV, and if we can do like a topological manipulation, which maps to another theory where the non-invertible defect becomes invertible, and then we can just run RG to the IR and to get some consequence in the IR. And then we can further use this inverse of the topological manipulation to get back to the original theory with non-invertible symmetry. So as we can see that if such a phi exists, then we can sort of understand the RG consequence of these non-invertible defects using a more roundabout way, which only involves the invertible defect. So this would motivate us to introduce a notion of intrinsically non-invertible defects. So more concretely, if a QFT equipped with a non-invertible defect, and there is a topological manipulation such that the non-invertible defect can be mapped to invertible defect by this topological manipulation, and then we will call this non-invertible defect as the non-intrinsically non-invertible. If such a phi does not exist, then we will call this non-invertible defect as intrinsically non-invertible. It turns out that the Symmetry TFT is a very useful tool in studying these kind of problems of telling whether a defect is invertible or not, is intrinsically invertible or non-intrinsically non-invertible. So what is the Symmetry TFT? So we start with a d-dimensional quantum field theory, which I call X, with a generic finite symmetry. So I'm not going to talk about the continuous symmetry. Let's just focus on the finite one, and it can be non-invertible. And such a theory can be blown up into a d+1 dimensional slab. So in the middle of the slab lives a Symmetry TFT, which is a topological quantum field theory in d+1 dimensions. And the boundary on the right is the boundary state, which encodes all the dynamics of the original d-dimensional quantum field theory. But the boundary condition on the right, on the left, is the topological boundary condition, and it's chosen to be the Dirichlet boundary condition. The advantage of using this Symmetry TFT is as follows. So it turns out that all topological manipulation of the theory X is in one-to-one correspondence with the choice of topological boundary condition on the left of the slab. For example, gauging the symmetry in the series X amounts to changing the Dirichlet boundary condition to the non-invariant boundary condition on the left of the slab. So from that, we see that the symmetry TFT itself is invariant under topological manipulations. So
there's actually a question in the
Yes.
chat whether this phi should always have an inverse, or is this an assumption? So I think this is more about the slide before, but you could also ask this here.
Yeah, as Justin mentioned, it's true that, for example, so as we know that the gauging has a inverse operation, which is the ungauging, and the stacking SPT is also invertible by stacking the inverse of the invertible series. Okay. Okay, so let's, so here I discussed the general properties of the symmetry TFT. So let's consider an example. Consider an example where a d-dimensional QFT has the finite invertible symmetry, G. So G is a group. And here we also allow G to be anomalous. So the anomaly is captured by the invertible theory labeled by a cocycle alpha. And so this theory, d-dimensional theory, should live on a boundary of d+1 dimensional invertible theory. And what is the symmetry TFT? The symmetry TFT is, this setup can be blown up into this setup, and the symmetry TFT living in the middle is the Dagor-Witten theory, whose Dagor-Witten twist is precisely labeled given by the anomaly alpha. So the action of, or the partition function of the Dagor-Witten model is simply sum over all the connections which are now made dynamical with the BTA, so the standard of BF coupling, and times the invertible so this is the standard of BF coupling, and this is the Dagor-Witten twist. And integrating on the B makes the A to be a cocycle. Okay. Okay, so given a QFT with a non-invertible defect, checking whether this non-invertible defect is intrinsically non-invertible, then reduce to asking whether this symmetry TFT is Dagor-Witten. Right. So in particular, concretely, when the non-invertible defect is non-intrinsically non-invertible, then the symmetry TFT must be a Dagor-Witten model, because the symmetry TFT is invariant under these topological manipulations. And if the non-invertible defect is intrinsically non-invertible, then the symmetry TFT cannot be a Dagor-Witten model. So this is so asking whether the non-invertible defect is intrinsically non-invertible or not, reduce to asking whether the symmetry TFT is Dagor-Witten or not. Okay, so here's the plan for the rest of the talk. In the rest of the talk, I'm going to explain how to use these criteria to tell us whether the non-invertible defect is intrinsically non-invertible or not, by studying a concrete example. The example is the 1 + 1 dimensional bosonic QFT with the Zn global symmetry. I have to mention that the symmetry TFT in this low dimension can be completely worked out by using the full machinery or full power of modular tensor category. However, because our ultimate goal is to understand the symmetry TFT in higher dimensions, so I'm not going to use the full power of the modular tensor category. In particular, I will not talk about the F symbol and R symbols and their consistent relation like the Haskell equations. Instead, I'm only going to focus on the fusion rules and the operator contents.
So just to ask, so in the higher dimensional case, the Dijkgraaf-Witten theory is could be some generalized Dijkgraaf-Witten theory for a higher discrete group.
Yes, yes.
Okay.
Yeah.
Thanks.
And okay, so let's start with the 1 + 1 dimensional QFT. Let's consider a 1 + 1 dimensional QFT X with the Zn symmetry. And we also require that this X is invariant under gauging Zn. Namely, X mod Zn is X itself. So because the theory is invariant under gauging the global symmetry, so it admits a non-invertible defect, namely the duality defect. So how to construct the duality defect? We just gauge the Zn global symmetry on half of the space and impose the Dirichlet boundary condition at the defect locus. So on the left of the space, we have the original system. On the right of the space, we gauge the one-form symmetry by summing over the background, by summing over this little b gauge field. And we still couple the theory, resulting gauge the theory back to this background field for the one-form symmetry, so that the entire system now is coupled to the same background field. Okay, so how to study the fusion rule of the duality defects? First, I'm going to talk about only focus on the 1 + 1 dimensional case and discuss its fusion rules and discuss its topological manipulations and try to answer whether this defect is intrinsically non-invertible. And then later I'm going to use the symmetry TFT to reproduce some of the results. And also, as well, going to see that it can also tell us new results. Okay, so the fusion rule of the duality defects can be worked out as follows. So we constructed two duality defects by considering this field theory configuration. And one defect is localized on x equals minus epsilon, and the other defect is localized on x equals plus epsilon. Considering the fusion rule just amounts to bring these two defects together and by taking this epsilon to 0. So the fusion product of the duality defect is defined by this theory configuration. So let's consider what this defect tells us. So on the right hand side, we can see that this B prime of gauge field is decoupled from the theory X. So we can sum it over. So in the interior of this X of this region, where X bigger than 0, we can integrate out this B prime gauge field, which will enforce that the little b is equal to the background field, capital B. Once we do once we integrate all this B prime, and we find that the right-hand side comes back to Zx of capital B. But such an integration, so integrating out the B prime, cannot be carried out on the defect locus. This is because the defect is defined such that the dynamical field satisfies this Dirichlet boundary condition. So we do not have this constraint at the defect locus. So instead, we need to sum over all the field configurations of little b, and this defines for us a one gauging of the Zn. So the defect for one gauging of Zn is precisely given by this condensation defect. We just need to sum over the Zn symmetry defect on the defect locus, which is just a one-dimensional locus. So we just sum over all the powers of the defect. So now this gives us this fusion rule, which is that the product of the duality defect fused with itself gives the condensation defect. Similarly, we can also work out the other fusion rules, and these fusion rules tell us that they satisfy the fusion rule of the temporary fusion of Zn fusion category. In particular, this also tells us that the duality defect is non-invertible, which has quantum dimension and square root of n. Okay, so now we know that the duality defect is non-invertible, but the question is whether it is intrinsically non-invertible. So in order to answer this question, we need to explore the space of topological manipulations. When n is prime, there is obviously only one topological manipulation, which is just gauging the entire symmetry Zn, because there's no subgroup of Zn. When n is not prime, the space of theory is very complicated. For example, we can gauge a normal subgroup, and the resulting theory will have this quantum symmetry Z hat P times the Zn over P with a particular mixed anomaly. And then we can further gauge with or without the twisted and discrete torsion, and the theory, the web of theory will become very complicated. So it's, especially when n is very large, it's very hard to check whether there exists a certain theory in the web which only has invertible defect. I have to, there's a side remark, which is that we only consider this bosonic theory, but for the fermionic series, one can also consider stacking SPT, which is the Arf invert. But in this talk, I'm going to focus on the bosonic case. Okay. Let's first consider this the simpler case when n is prime. So to check whether the duality defect is intrinsically non-invertible, we just need to apply this topological manipulation, which is the gauging of the entire Zn onto this, which is given by S, onto the duality defect. So we start with the duality defect, like defined like this, and then we gauge the Zn symmetry on the entire setup. And by properly massaging these expressions, we see that the resulting defect is still a duality defect, but it acts on another theory, S of X. So we conclude that this duality defect, upon this particular topological manipulation, maps back to itself. So it's not intrinsically non-invertible. But for non-prime, because the web of defect is very complicated, so we cannot immediately conclude that this theory is, this duality defect is intrinsically non-invertible or not. So now the symmetry TFT comes to help. Okay, so before we directly proceed to the symmetry TFT for the entire symmetry, including the duality defect, let's first consider a simpler case where we only consider the symmetry TFT for the Zn symmetry. So let's first relax the self-duality under gauging Zn and just require that the theory X in 1+1 dimension it has the Zn symmetry. So as we mentioned in the beginning of the talk, because the theory only has an invertible symmetry, the symmetry TFT is just a Dagger-Witten theory. But here, because the Zn does not have anomaly, it's the Dagger-Witten theory without twist. So it's a Zn gauge theory. So the action is very simple. It's just like this. And let's review the property of this Zn gauge theory itself, and then study the topological boundary conditions. And we're also going to reproduce the fusion rules from the symmetry TFT point of view. Okay, so let's review the property of this Zn gauge theory. The Zn gauge theory has n square number of non-topological line defects labeled by a pair of Zn quantities, E and M. And gamma is the line where the defect lives on. And the L1, 0 line and the 0, 1 line generates the Zn times Zn one-form symmetry. There is also a EM exchange zero-form symmetry, which flips the A and B. Flipping A and B leaves the action invariant, so it's a symmetry. And on the operators, it just exchanges the E and M labels. So it maps the E, M line to M, E line. Pictorially, this zero-form symmetry defect, which is a codimension 1 defect, which is a surface, acts on the line like this. So when a E, M line comes in from the left, and M, E line goes out on the right. I have to say that there are many other codimension 1 defects in this Zn gauge theory, and most of them are non-invertible. And the full list of defects has been studied in this not very nice paper. But in this talk, I'm only going to focus on this simple invertible codimension 1 surface. As advertised in this paper, every codimension 1 topological defect is a condensation defect. And in order to understand why it's a condensation defect, let's consider this intuitive picture. So as I said, what this Z2EM defect, which I call DEM, does is that when E, M line goes in and M, E line goes out, we can use the folding trick to fold the line on the right-hand side to the left. And after flipping the orientation, we find that some copies of 1, -1 line can be absorbed into this surface. So it means that it gives us an intuition that this codimension 1 line, codimension 1 surface is a condensation defect of this 1, -1 line. And indeed, in this paper, they have a explicit expression for this condensation defect. And indeed, one can check that when we do this parallel fusion of the defect, so if we fuse this E, M line parallel to the defect, and what we get is is the M comma E line fused with the defect, same defect, but from the other side. And we can also explicitly check that this condensation defect square to identity of it. Okay, so far for the operators in the bulk, let's also consider the boundary conditions. So as I said, every 1 + 1 dimensional QFT with Zn global symmetry can be blown up into a slab where there is a Zn global Zn gauge theory living in the slab, and with a Dirichlet boundary condition on the left and non-topological boundary condition on the right. Let's discuss what this Dirichlet boundary condition does for the line operators in the bulk. For the Dirichlet boundary condition, the 1, 0 line, Dirichlet boundary condition is given by enforcing the A gauge field, which is dynamical in the bulk, at the boundary is capital A, which is the background field. And this 1, 0 line is given by e to the IA times 2 pi over n. So 1, 0 line, when we put it parallel to the boundary, it can be absorbed into the topological boundary. But if we put it orthogonal to the boundary, then it can end on the topological boundary. However, the 0, 1 line, which is the exponent of I times integral of B field, when we put it on the parallel to the boundary, it cannot be absorbed, and it also cannot end on the boundary if we put it orthogonal to the boundary. So as a consequence, upon shrinking the slab, and the 0, 1 line survives as the symmetry operator of the Zn of the series X, which generates the Zn symmetry. But the 0, 1 line, the only way it can survive is that we put it on orthogonal to the boundary, and upon shrinking, it becomes a point operator. And because it has to end on the non-topological boundary side, so this point operator is not necessarily topological. So it's in general, it's an order parameter of the Zn, but it's in general non-topological. We can also consider the non-invariant boundary condition. The non-invariant boundary condition can be obtained by composing the Dirichlet boundary condition with this DEM surface. So when we put this DEM surface parallel to the boundary in the bulk, we can push this DEM surface to the boundary and fuse with the Dirichlet boundary condition. And as a consequence, we'll get the non-invariant boundary condition. And if we further shrink this slab, we'll instead not get a series X, the original series, but instead get a series X mod Zn. And with the non-invariant boundary condition, the role of these line operators are exchanged. So now this 1, 0 line, becomes the symmetry operator in the series X mod Zn. So it's a quantum symmetry operator. So 0, 1 line becomes this symmetry order parameter for this quantum symmetry generated by eta hat. Okay, so far we only discussed operators, surface operator, which does not have boundary, but we can also consider the surface operator with an open boundary condition. So in particular, yeah, so this is what's called the twist defects in the condensed matter literature. So the DEM defect, which generates the Z2 EM symmetry, can be opened up with a Dirichlet boundary condition for the condensate. And this defines for us a vanilla twisted defect, which I call the sigma 0. So we can view it as a non-genuine line defect, which is attached to a surface. And this surface is the symmetry defect for the Z2 EM symmetry. There's another interesting point of view of the twisted defect, which is that the twisted defect can be understood as the one gauging of this L1, -1 line on half of the codimension 1 submanifold. So this should be contrasted with the ordinary duality defect, where we gauge the symmetry on half of the entire space-time. But here, we only gauge the symmetry generated by this 1, -1. We only on half of the codimension 1 submanifold. So this is the one gauging. This is a combination of higher gauging with the gauge only on half space. So this motivates us to interpret this twisted defect as the higher duality interface. I will not call it a higher duality defect, but rather a higher duality interface, is because in this two-dimensional manifold, the left of this line and the right of this line are generally different. But later, we are going to gauge the Z2 EM symmetry so that this surface will be invisible. And then this higher duality interface will become a higher duality defect. Okay, so here is so far for the vanilla twisted defect. We can further generate a new twisted defect by further fusing the invertible line defects labeled by E, M parallel to this boundary. And this will give us the new defect, which turns out to depend only on the sum of E and M. So in total, we have n number of twisted defects. Okay. So we can put this twisted defect into the slab. And what it does for us is that upon compactification, upon shrinking, it will give us an interface between the series X and the series X mod Zn. This is because if we focus on the upper half of the setup, upon shrinking, we get series X. If we focus on the lower half of the setup, upon shrinking, and because there is a DEM surface defect inserted in the slab, as I mentioned in the previous slide, the resulting series is X mod Zn. So in the middle, we get a topological interface between the two series.
Can I ask a question?
Yes.
Can EM end on the boundaries in either of them?
EM end on the boundary. Here we do not choose to end it on the boundary, but you can.
But could it? Yeah, usually could.
Yeah. Okay. So now, because we want to consider the fusion rule of this topological interface, and it turns out that the fusion rule of topological interface can be induced from the fusion rule of the twisted defect. So let's first talk about the fusion rule of the twisted defect. So as we said, the twisted defect is just the one gauging of this 1, -1 defect on half of the codimension 1 surface. If we fuse the two of such defects together, we just get a two gauging of the symmetry generated by the same operator. So we immediately get this fusion rule. And further, and the fusion rule of more other variants of the twisted defect can be obtained from this one by further fusing the invertible defect. Okay, so having discussed the fusion rule of the twisted defect, let's shrink the slab and talk about the fusion rule of the duality interface. So upon shrinking the slab, we get this, as we mentioned, the Zn symmetry generator is given by 1, 0, 1 line, which will denote as the eta in the series X. And the 0, 1, 0 line will become the will become a symmetry generator for the dual quantum symmetry in the series, in the gauged series. And the twist operator, the twisted defect upon shrinking will provide us a topological interface between the two series, X and X mod Zn. And we can work out the fusion rule of these operators upon which we get after shrinking from the fusion rule that we discussed in the previous slide. And here is the result. And if we further assume that the series is self-dual, namely X and X mod Zn are the same series, then we can identify this symmetry defect with the quantum symmetry defect. And the fusion rule will be simplified as this. And this is nothing but the fusion rule for the temporal Yamagami category of Zn. So far, we have reproduced the fusion rule, which we obtained from another perspective just in 1+1 dimensions. And here, we reproduce the fusion rule from the Symmetry TFT point of view. Okay, so far, I haven't assumed that the series X is self-dual, except in the last step. And now let's further require that the series X is self-dual and consider the Symmetry TFT for the entire fusion category, which is the temporal Yamagami of Zn. In order to tell whether the duality defect is intrinsically non-invertible, as I said, we would like to find the symmetry TFT involving the duality defect and just check whether the symmetry TFT is a Dagor-Witten series or not. So here's the claim. The claim is that in order to find symmetry TFT for this temporal Yamagami of Zn, we just start with the symmetry TFT for Zn, which is the Zn gauge series, and then we simply gauge the EM global symmetry, zero-form global symmetry. Such the resulting series comes with the various names. In this condensed matter paper, it's called a twisted liquid. In this condensed matter paper, it's called a G-equivalentization of the G-cost unitary modular tensor category. And in these mass papers, it's called the Dreamfield Center for temporal Yamagami of Zn. So let's understand why do we need to gauge the Z2EM symmetry in a more intuitive way. So here is the setup before gauging. We can get a topological interface between the two series by putting a twisted defect in the middle of the slab. But because we want to get not an interface, but a defect within one series, so we really want to get rid of the, we really want to let this boundary condition to be the same, let these two series on the two sides to be the same. So we really need to get rid of the surface attached to the twisted defect. So how to get rid of the surface attached to the twisted defect? we just gauge the Z2EM symmetry. So after gauging, the theory in the bulk is changed. It's no longer a Z2 gauge theory, but it's a more complicated theory, which is described by the Gentile Center for the Yamagami LZM. Okay, so for our purposes, it's sufficient. So we just want to know whether this symmetry TFT for this fusion category is Degard-Witten or not. So we will not care about the boundary conditions for now. We'll just put this symmetry TFT on the closed three-dimensional manifold and talk about the operator contents and the fusion rules, etc. So before gauging the EM symmetry, we have the following line operators. So we have n-squared line operators. They are all invertible ones. And one invertible surface operator, which is the symmetry defect for Z2EM, and n-twist defects. So gauging the EM symmetry has been understood in these papers, and it amounts to three-step process. First, we need to keep the lines which are invariant under the Z2EM and drop the ones that are not. And then we need to promote the twisted defects, which are line operators, non-genuine line operators attached to the surface, to genuine line operators by forgetting about the surfaces. And then we further need to attach the quantum line operator coming from gauging the Z2EM to these line operators. Applying this three-step process to this particular ZN gauge theory, we get the following line operators. So we have the 2n number of invertible lines with quantum dimension 1. They come from E, E line invertible lines. And further Q is labeled by whether we attach the quantum line operator or not. And we also have n times n minus 1 over 2 number of non-invertible lines of quantum dimension 2. They come from the direct sum of EM plus ME line before gauging, where E and M are chosen not to be the same. And lastly, we also have 2n number of non-invertible lines of quantum dimension n, and they come from the twisted defect by forgetting about the surface attached to a twisted defect. For example, when in the case when n equals to 2, it's well known that the symmetry TFT of the temporary of Z2, which is the Ising, is the Ising times Ising bar. And because Ising has 3 lines, so in total we have 3 times 3 is 9 lines. And indeed, by summing over these numbers, we indeed get 9 lines. So this is what I mentioned before. So before gauging, we have the twisted defect, which can be interpreted as the higher duality interface by one gauging of the 1 minus 1 line on half of the codimension 1 space. And if we further gauge the Z2EM symmetry, this surface is invisible in the gauged theory, and this higher duality interface becomes a higher duality defect, which is a codimension 2 defect. We can also discuss the fusion rule of these lines I listed in the previous slide. I will not discuss the fusion rule explicitly in detail, but just to mention that the fusion rule involving the lines with integer quantum dimension has been worked out nicely in this paper. And it turns out that fusion rules involving this square quantum dimension square root of n length can also be determined, but in a slightly different way. Okay, so let's finally come back to our initial problem, which is the duality defect defined by gauging Zn intrinsically non-invertible? Remember that our strategy is that if the non-invertible duality defect is non-intrinsically non-invertible, if the symmetry TFT is Dirac-Witten, if it's intrinsically non-invertible, if the symmetry TFT is not Dirac-Witten. In order to proceed, let's use a fact, which is that the topological lines in 2+1 dimensional bosonic Dirac-Witten series have integer quantum dimension. And also by combining the fact that the symmetry TFT we obtained contains the lines with quantum dimension square root of n. And by comparing with this fact, we immediately conclude that when this n is not a perfect square, then the symmetry TFT is not a Dirac-Witten, and therefore the duality defect is intrinsically non-invertible. And indeed, when n is a prime number, as we concluded in the earlier part of the talk, it's intrinsically non-invertible. And indeed, this is consistent with this observation from the symmetry TFT point of view. Of course, I have to mention that this is only a sufficient condition, but not a necessary condition. In other words, if this integer n is a perfect square, it does not tell us that the symmetry TFT is non-intrinsically non-invertible. In order to tell that, we need to use more data like the braidings and fusion, braidings and other more refined data of the modular tensor category. Okay, so let me summarize. In this talk, we found that the fusion rule of the duality interfaces and duality defects can be seen from the symmetry TFT point of view. And using the symmetry TFT for the duality defects, we are able to determine, at least partially, when it is intrinsically non-invertible. We also see an interesting example of higher duality defects or higher duality interface by higher gauging on half of the codimensional half space, higher codimensional half space. The results, the discussion in the talk can be easily generalized to other systems. For example, the 1+1 dimensional bosonic QFT with this more complicated symmetry. And the result is that if the duality defect defined by gauging this entire symmetry is intrinsically non-invertible, if this n1 times n2 is not a perfect square. And indeed, when n1 and n2 are equal, and especially when they are equal to 2, it's known that this is not intrinsically non-invertible. In other words, we can find a topological manipulation which maps the series, which maps the duality defect to invertible one. There are several obvious generalizations. In this talk, I only discussed the fermionic series of bosonic series. Then how about the fermionic ones? I only talk about this simplest case where the dimension is 1+1, and but it's obvious to ask what happens when the dimension is higher than 1+1, especially 3+1 duality defects in the 3+1 dimensional series. And I only discussed the duality defects. Then how about the chirality or unality defects? And moreover, there's also a Lagrangian formulation for the symmetry defect by the twisted cochain or twisted cocycle, and Justin mentioned it briefly in his talk at the PI conference. So that's it. Thank you very much for your attention.
Thanks very much for this really nice talk. And are there questions from the audience?
Yeah, sorry, can I ask a question?
Yes.
It seems that for any codimension 1 topological defect in the bulk, like the Z2 electromagnetic, you always get exactly one twist defect. Is it right?
Yes. So sorry. So here we have a Z2 symmetry in the bulk, and we get untwisted defect.
Oh, okay.
But yeah, you can do the higher gauging and impose the Dirichlet boundary condition on half of the space, and this will give you a vanilla twisted defect. And you can, starting from this, you can further fuse with the lines and get new twisted defects.
Okay, I see.
Yeah.
But the duality defect is the one in which you do not fuse, right?
Sorry, can you say again?
The duality defect is the one which is
yes. I didn't mention it in the talk. So we have untwisted defect in the bulk, but when you fuse it with the Dirichlet boundary condition on the left, all the twisted defects will reduce to one twisted defect. So you only get one duality defect in the end.
Okay, I see.
Yes.
Can you make a comment how this fits together with the Symmetry TFT description with this twisted co-cycle that Justin was mentioning?
Yeah, we are still working on it.
Okay.
There are some.
You don't have to. I don't want to.
Yeah. Well, there's yeah.
Okay, so it's still something to be clarified. Any other questions, comments? So maybe we just first thank Yunqin for this really nice talk, and then we can switch off the recording and then ask all the stupid questions that we don't want to be on record.